Hello dear students, so welcome to Gate Wallah. Okay, so in this particular session we will discuss about the steady state conduction heat transfer in the cylindrical coordinate system and the spherical coordinate system, right? In the previous lecture we had discussed about the general heat conduction equation in the Cartesian coordinate system. Now in this session we will discuss about the cylindrical coordinate system and the spherical coordinate system. So what topics we will cover? What topics we will cover in this session? We will start our discussion on general heat conduction equation in the cylindrical coordinate system. Then we will discuss the conduction heat transfer through the hollow cylinder. After that we will discuss the solid cylinder with the internal heat generation. Right. So this is all about the cylindrical coordinate system, and similar thing we will discuss in the spherical coordinate system also. So first we will start our discussion on general heat conduction equation in the spherical coordinate system, right? After that we will discuss the conduction heat transfer, or I can say rate of conduction heat transfer through the hollow sphere. Hollow sphere, na? This is not hollow cylinder, this is hollow sphere. This is not hollow cylinder, this is hollow sphere. Hollow sphere. And then we will discuss the solid sphere with internal heat generation. Solid sphere with internal heat generation. Solid sphere with internal heat generation. Okay. So let's start today's session. On general heat conduction equation in the cylindrical coordinate system. Right. So first, to understand the cylindrical coordinate system, first to understand the general heat conduction equation in the cylindrical coordinate system, first try to understand, if I want to locate a point in a cylindrical coordinate system, then what parameters are required, right? In the Cartesian coordinate system, if I want to locate a point in a Cartesian coordinate system, then x, y, z are required, right? In a similar fashion, if I am talking about the cylindrical coordinate system, then what parameters are required, right? So in the cylindrical coordinate system, that r, theta, or you can say r, phi and z are required. R, phi and z are required. So what is the r? R is the radial distance. If I want to locate a point in a cylindrical coordinate system, then radial distance is required. That first radial distance is required, right? So let us assume there is a cylinder. This is the cylinder, and if I want to locate a point, okay, see, let us assume, see, if I want to locate this point, then what parameters are required? See, first is a radial distance. That point may be here, the point may be here if cylinder is large, right? So if cylinder is large, then that point may be here, right? So first thing that required is the radial distance. And what is the limit of the r? The limit of the r is from 0 to infinite. What is the limit of the r? The limit of the r is 0 tends to infinite. So first I draw here a cylinder. So let us assume this is a cylinder. This is the cylinder. Okay, so this is the cylinder. Z, Y, X, right? And I want to locate a point in a cylindrical coordinate system, right? So this point is P. So what parameters are required? R, phi and Z, right? R, phi and Z. So first parameter that is required is a radial distance. And what is the limit of the r? The limit of the r is 0 to infinite. The cylinder, This cylinder may be of radius of 10 centimeter, this cylinder may be of radius of 50 centimeter, this cylinder may be of radius of 100 centimeter, right? So first parameter that is required is a radial distance, right? Now see, if I fix the radial, if I fix the radius, let us assume radius is fixed, okay? Now focus on this plane, focus on this plane, focus on this plane, focus on this plane. Okay, this is the xy plane. If you see this diagram, so this plane is the xy plane, this plane is the xy plane, and in the xy plane, right, circle is observed, na? In the xy plane, the circle is observed, right? So see, in xy plane, this circle is observed. Okay, this is a circle in xy plane. So this is the x-axis and this is the y-axis. I am talking about the xy plane now, and in xy plane circle is observed. Okay, now this is x-axis and this is y-axis. Fine. I fix the radius. So radius is fixed. Right. R is fixed. Now focus. Focus on the board. See here. That point. Right. That point R is fixed. Right. We fix the R. And in this plane, see, in this plane, that point may be here, that point may be here, that point may be here, right? So the second parameter which is required is the phi. Right? So that point may be here, that point may be here, that point may be here, that point may be here. That means on a circumference, that point may be anywhere. Right? So this is the x-axis, is the reference axis. So I am considering here that phi is 0. So see, if I want to locate a point in a xy plane, then R is required, and the second parameter which is required is the angle. Right? And what is the reference for that angle? That x-axis is the reference. So phi is equal to 0 on the x-axis, and that point may be anywhere. Here, right? So let us assume that point may be here. And this angle is phi. So what is the limit of the phi? That limit of the phi is 0 to 2 pi. 0 to 2 pi, 360 degree, right? So in the xy plane, the two parameters are required. First one is the R, and the second one is the phi. These two parameters are required. Okay, but I want to locate a point in a space. That means, see, I want to locate this point. Now see, if you see, I fix the R. Now, if I fix the R, let us assume that point is here. That means phi is also fixed. In this plane, I am considering that point is here. So R fixed, phi fixed. Now see, in the space Z is also required, na? Right? So perpendicular to the monitor, see, now see, the point may be here, that 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 point may be here. So if I fix the R, if I fix the phi, then that point may be here, maybe here, maybe here, maybe here. That means at any Z, na? At any Z. Right? So three parameters are required if you want to locate a point in a space in the cylindrical coordinate system, then three parameters are required. And if you want to locate a point in the xy plane, then only two parameters are required. In plane, two parameters are required. So if I am talking about the xy plane, in xy plane, that R is required and the phi is required. Whereas in space, right? See, that point, right? So perpendicular to the monitor. So let us assume there is a cylinder. Let us assume there is a cylinder. Let us assume there is a cylinder like that. See, if you see only this face, na? If you see only this face, na? Right? Okay. So perpendicular to the board, there is a cylinder. Now this point may be here, 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 this point may be here. Right. So the third parameter that is required is a z. So what is the limit of the z? What is the limit of the z? The limit of the z is minus infinity to plus infinity. Minus infinity to plus infinity. Right. That point may be above also, that point may be below also. So minus infinity, or sorry, plus infinity to minus infinity. So three parameters are required, r, phi and the z. So I hope you are able to understand this thing. In cylindrical coordinate system, the three parameters are required, and that is r, phi and the z. Right. Now, if I am talking about the general heat conduction equation, so in the Cartesian coordinate system, the temperature varies with respect to r. The temperature, in Cartesian coordinate system, the temperature varies with respect to space. In space, that means x, y, z, and time tau. Similarly, if I am talking about the general heat conduction equation in the Cartesian coordinate, general heat conduction equation in cylindrical coordinate system, in cylindrical coordinate system. So temperature is function of space and the time tau. Temperature is function of space and the time tau. And if I am talking about the space, then temperature is function of r, phi, z, and time, that is tau. Temperature is function of r, phi, z, and time tau. Okay, so the general heat conduction equation in the cylindrical coordinate system we can write in this way, right? That come from the energy balance, no? That come from the energy balance. I already discussed this part, right? So I'm directly writing the general heat conduction equation in the cylindrical coordinate system, right? So the general heat conduction equation in the cylindrical coordinate system is, that is 1 by r del by del r k r del t by del r del t by del r plus 1 by r square del by del phi k phi del t by del phi plus del by del z kz del t by del z plus q dot g is equal to, that is rho c del t by del tau. Okay, so first term shows the variation of temperature with r. The second term shows the variation of temperature with phi, that means in the circumferential direction. The third term shows the variation of temperature in the direction of z, that means in the axial direction. The fourth term shows the internal heat generation, or the fourth term incorporate the internal heat generation. That fifth term shows the variation of temperature with respect to time. Right. Now, so far I am not considering any assumptions. I am not taking any assumptions. right? This is the general heat conduction equation in the cylindrical coordinate system. Now I am assuming that material is homogeneous and the isotropic. I am assuming that material is homogeneous and isotropic. Material is homogeneous and isotropic. Material is homogeneous and the isotropic. If I am assuming material is homogeneous and isotropic, that means that Kr is equal to K phi is equal to Kz is equal to that is K. So ultimately what you are getting, right, that 1 by R del by del R del T by del R plus 1 by R square del square T by del phi square plus del square T by del Z square plus Q dot G by K is equal to 1 by alpha del T by del tau. 1 by alpha del T by del tau. And what is the alpha? That alpha is a thermal diffusivity. That alpha is thermal diffusivity. Is it clear? Okay. Now see, from here we can write the Poisson equation also, we can write the Laplace equation also, we can write the diffusion equation also, right? We already discussed all these three equations in the Cartesian coordinate system, right? So what is the Laplace equation? What is the Laplace equation? That Laplace equation. What is the Laplace equation? So that Laplace equation is steady, right? Steady plus no internal heat generation. No internal heat generation, right? If steady state condition is maintained and there is no internal heat generation, that means this term is 0 and this term is 0. So ultimately what you are getting, this term plus this term plus this term is equal to 0, and that is a Laplace equation. That is a Laplace equation, right? Now come to the second. The second is a Poisson equation. Second one is a Poisson equation. So what is the Poisson equation? Poisson equation. So what is the Poisson equation? The Poisson equation is steady plus with internal heat generation. With internal heat generation. So if I am talking about the Poisson equation, so in Poisson equation, this term is vanished, no? This term is vanished, this term is finished. So only this term, this term, this term and this term are present. Okay, so this term plus this term plus this term plus this term is equal to 0. That is a Poisson equation. Okay, now what is the diffusion equation? Diffusion equation. So what is the diffusion equation? Diffusion equation. So diffusion equation is unsteady plus no internal heat generation. If unsteady, that means this term is present. No internal heat generation, this term is vanished, right? So this term plus this term plus this term is equal to 1 by alpha del T by del tau, and that is a diffusion equation. Okay, now come to the next. I am considering some assumptions here, right? And according to that, reduce the general heat conduction equation in a simple form, right? So what assumptions I am taking here? What are the assumptions that I am taking here? So that first assumption, is material is homogeneous and the isotropic. That is a common assumption. Material is homogeneous. Material is homogeneous and isotropic. material is homogeneous and isotropic. Right, this is the first assumption. The second assumption is steady state, or I say the second assumption is one dimensional. And in one dimensional, the direction that is considered is radial direction. Radial direction. Radial direction. Third assumption is steady state. Third assumption is steady state. Fourth assumption is no internal heat generation. No internal heat generation. That fifth assumption is thermal conductivity is constant. Thermal conductivity is constant. So if I am considering all these assumptions, then can we reduce the general heat conduction equation in a simple form? Can we reduce the general heat conduction equation in a simple form? Yes, sir, we can reduce. Right. So material is homogeneous and the isotropic. That means Kr is equal to K theta is equal to K phi. One dimensional, that is only radial direction. That means circumferential direction and the axial direction term is vanish. Steady state, that means del T by del tau is vanish. No internal heat generation, that means Q dot G term is not there. So ultimately, general heat conduction equation is reduced in a simple form, and that is 1 by R del by del R del T by del R is equal to 0, or we can write the partial derivative in terms of total derivative, because temperature is only function of R na. Under these assumptions, that temperature is only function of R na, temperature is only function of R. So we can write in this way also, 1 by R d by dr R dt by dr is equal to 0. Okay, so this is also a general heat conduction equation under these assumptions. This is also a general heat conduction equation under these assumptions. Sometimes this equation is written in another form. And what is that form? Okay, I am considering this is equation number A. Right. Sometimes this equation is written in another form. And what is that form? Right. See, that is 1 by R. 1 by R. Now, differentiate here. Apply that formula, differentiation of UV, differentiation of UV, U constant, then you differentiate the V constant, then you differentiate the U, right? That thing only, right? So here that R constant, this is d square T by dr square plus then dt by dr is constant, and differentiation of R, so that is 1, and this is equal to 0. So ultimately what you are getting, this 1 by term is inside, so ultimately you are getting d square T by dr square plus 1 by R dt by dr, 1 by R dt by dr, and this is equal to 0. So this is also a general heat conduction equation, okay, under these assumptions. Okay. So this equation, or I can say that equation number A, you can write in this form also. You can write in this form also. That means in the form of equation number B. Is it clear? Okay. Now, so from equation number A, come to the equation number A. From equation number A, I want to find out the temperature variation with R. So that is 1 by R d by dr R dt by dr is equal to 0. Right. Now see, so this equation is reduces in this form, the d by dr r dt by dr is equal to 0, is equal to 0. Now integrate it. If you are integrating, what you are getting, that r dt by dr is equal to integration constant, that is c1. Integration constant, that is c1. So from here you can write that dt by dr is equal to, this is c1 by r, c1 by r. Now integrate once again, integrate once again, integrate once again, integrate once again. So that is t of r is equal to, this is c1 ln r plus c2, right? So this is the temperature variation with r. This is the temperature variation with r. And the c1 and c2 are integration constant. c1 and c2 are integration constant, integration constant. c1 and c2 are integration constant, right? And these integrations are calculated, these integration constants are calculated by using the boundary condition, and the boundary condition is according to the problems, right? So c1 and c2 are integration constant which are calculated, or which are calculated by using the boundary condition, by using the boundary conditions, by using the boundary condition, by using the boundary condition. Fine. Now see here, I am considering a problem that is for hollow sphere. I am considering a problem that is based on the hollow sphere. Hollow cylinder. Hollow cylinder. I am considering a hollow cylinder. Hollow cylinder. Okay, so this is the hollow cylinder. This is a hollow cylinder. Perpendicular to the board, or perpendicular to the monitor. Perpendicular to the monitor, the length is L. Right? Perpendicular to the monitor, the length is L. Right? So this is a hollow cylinder. This is the center. This radial distance is R1. This radial distance is R2. This radial distance is R1. This radial distance is R2. Okay? And at any R, the temperature is T. Sorry, and at any radial distance that is R. That is R. And I assuming that at R is equal to R1, at R is equal to R1, the T is equal to T1. At R is equal to R2, T is equal to T2. Right? And at any radial distance, at any radial distance R, temperature is T. Temperature is T. At any radial distance, the temperature is T. Is it clear? And thermal conductivity of this hollow cylinder, that is K. K is the thermal conductivity. K is the thermal conductivity, right? And I want to find out the temperature variation with R, because I already told you in conduction heat transfer there are two objectives. In conduction heat transfer there are two objectives. The first objective is find the temperature variation with respect to space, right? And the second objective is find the rate of conduction heat transfer. So if you are considering all these assumptions, if you are considering all these assumptions, then temperature is the only function of R. So here in case of the hollow cylinder, that first objective is find the temperature variation with respect to R, and after finding it, right, find the rate of conduction heat transfer through this hollow cylinder, right? So I am assuming here that T1 is greater than T2. I am assuming here T1 is greater than T2. If T1 is greater than T2, then then the rate of conduction heat transfer is Q dot from this hollow cylinder. Is it clear? Is it clear? Okay. Now see, shall we start our discussion from here? Shall we start our discussion from here directly? Because I already simplify this general heat conduction equation, simplify the general heat conduction equation. So shall I start from here? That right? So T of R is equal to C1 ln R plus C2. C1 and C2 are integration constant, right? And integration constant are calculated by using the boundary conditions. So what are the boundary condition here? These two boundary condition at R is equal to capital R1, T is equal to T1. So directly I can write here that T of R is equal to C1 ln R plus C2. So use the first boundary condition. So from the first boundary condition that T is equal to T1, and this is the C1 ln R1 plus C2. Use the second boundary condition. So that is T2 C1 ln R2 plus C2. So here two equation and two unknowns. Okay, two equation and the two unknowns. You can easily find out the C1 and the C2. You can easily find the C1 and C2, right? Two equations are here, two equations and two unknown. You can easily find out the C1 and C2, right? And after finding the C1 and C2, put that C1, C2 in this expression. This is the equation number A, na? This is the equation number A, or see, this is the equation number 1, I say. This is the equation number 1. Equation number 1. After finding the C1 and C2, right, put that C1 and C2 in the equation number 1. And after putting what you are getting, that directly I am writing here, right? So that is T of R is equal to T1 upon T2 minus T1, and that is equal to ln R minus ln R1 divided by ln R2 minus ln R1, right? Or you can write in this way also, that is equal to, that is ln R by R1 divided by ln R2 by R1. Right. So from this expression, it is very much clear that temperature variation with R is logarithmic variation. How the temperature varies with respect to R? The temperature varies with respect to R logarithmically. So logarithmic temperature variation. Logarithmic temperature variation. Logarithmic temperature variation with R. So if, see here, See, here the temperature is T1 na? Here the temperature is T1. Here the temperature is, let us assume this is T2. So the temperature variation with respect to R, that is logarithmic variation. So this variation is logarithmic variation. This variation is logarithmic variation. This variation is logarithmic variation. Is it clear? Is it fine? So that first objective is find the temperature variation with respect to space, right? So here I calculate or I find the temperature variation with respect to R. So that is the first objective. Now what is the second objective? The second objective is rate of conduction heat transfer. What is the rate of conduction heat transfer through this hollow cylinder? Rate of conduction heat transfer through this hollow cylinder. Rate of conduction heat transfer through this hollow cylinder. Rate of conduction heat transfer through hollow cylinder. Rate of conduction heat transfer through hollow cylinder. Right? Now see. Hollow cylinder. Now see here. Again I am considering a hollow cylinder. Hollow cylinder. The length is perpendicular to the monitor. Okay? Length is perpendicular to the monitor. Okay. So this is the radius R1. This is the radius R2. This is radius R1 and this is radius R2. Okay. And at any radial distance R, I am considering a very small thickness, element at any radial distance R. See, just 1 minute. Okay. At any radial distance R, I am considering a small elemental ring, that is R. And what is the thickness of this small elemental ring? That is dr. Or this small element, that is dr. Right? The thickness is dr. Right? And across this small element, the temperature difference is dt. Across this small element, the temperature difference is dt. Across this small element, the temperature difference is dt. Right? That means, if you see here, this is a small element na, this is the center na, radial distance r, this is a small element, the thickness is dr na, this thickness is dr. And here the temperature is T plus dt. Here the temperature is T. So what is the temperature difference? The temperature difference is dt na, right? And from this small element, the rate of conduction heat transfer. From this small element, the rate of conduction heat transfer is dq dot. That is dq dot. Whereas the rate of conduction heat transfer from this hollow cylinder is q dot, right? At r is equal to r1, we already told you, at r is equal to r1, at r is equal to r1, t is equal to t1, at r is equal to r2, that t is equal to, that is t2, that t is equal to t2 and t1 is greater than t2. T1 is greater than T2. I am assuming this. T1 is greater than T2. So what is the relation between this Q dot and dQ dot? What is the relation between the Q dot and dQ dot? So from this diagram, it is clear whatever the rate of conduction heat transfer occurs from this hollow cylinder, the same rate of conduction heat transfer occurs from this small element also. See here, right? That Q dot from this cylinder, from this hollow cylinder, the rate of conduction heat transfer is Q dot. And from this small element, the rate of conduction heat transfer is dQ dot. And from this figure, it is very much clear, right, that Q dot is equal to dQ dot only. That dQ dot, what is the relation between the Q dot and the dQ dot? So Q dot is equal to dQ dot. Q dot is equal to dQ dot. Right. So shall we apply the Fourier law of heat conduction to find the rate of conduction heat transfer? Yes, sir. So from Fourier law of heat conduction, from Fourier law of heat conduction, from Fourier's law of heat conduction, heat conduction, right, that Q dot is equal to, that is minus K, or simply first you can write dQ dot, that is for a small element, na? dQ dot is equal to, that is minus Ka dt by dr, minus Ka dt by dr, okay. And relation between dQ dot and Q dot is dQ dot is equal to Q dot, so we can directly write Q dot is equal to, that is minus Ka dt by dr. We already know the temperature variation, na? That T minus T1 upon T2 minus T1, and that is ln R by R1 divided by ln R2 by R1, right. So ultimately what you are getting this T1 plus T2 minus T1 ln R by R1, right, ln R by R1 ln R2 by R1. Fine. Now find the dt by dr here. Find the dt by dr from here and put here. So Q dot is equal to, that is minus K. What is the A? Right. First, what is the A? What is the area? What is the area from where the conduction heat transfer occurs? What is the area? So that area is 2 pi r into L, na? This is the area, na? 2 pi r into L, na? Right. This is the 2 pi r and perpendicular to the monitor, the length is L, na? So what is the area from where the conduction heat transfer occurs? The conduction heat transfer occurs from the area, that is 2 pi r into L, right. This is a 2 pi r and perpendicular to the monitor, the length is L, na? The conduction heat transfer occurs like this, na? The conduction heat transfer, see, this is a solid cylinder, oh sorry, this is a hollow one, na? If you see from inside, that is a hollow. So that conduction heat transfer occurs in this direction, So what is the area? This area is, this is the 2 pi r, this is the 2 pi r, and this is the length, right. The conduction heat transfer occurs like this, na? Conduction heat transfer occurs like this, na? So this is 2 pi r into L. Is it clear? Is it clear? 2 pi r into L, right. So from here, this K is 2 pi r L, and calculate the dt by dr from here. So dt by dr is equal to, the first term is 0, T2 minus T1, right, ln R. So that is 1 by R, right, and that is ln R2 by R1, ln R2 by R1, right. So ultimately what you are getting, that minus K 2 pi R, and this is T2 minus T1, T2 minus T1 1 by R, and that is ln R2 by R1. Okay, so R cancel out. So ultimately what you are getting, that is T1 minus T2, T1 minus T2, and we can arrange this term in this way, ln R2 by R1 divided by ln R2 by R1 divided by, that is 2 pi KL. This is 2 pi KL, and this is the rate of conduction heat transfer from the hollow cylinder. Okay, so I write here that Q dot is equal to, this is T1 minus T2 divided by ln R2 by R1 by, that is 2 pi KL. And if you are comparing this rate of conduction heat transfer through this T1 minus T2 divided by RTH, thermal resistance. So what is the thermal resistance in this case? In case of the hollow cylinder, the thermal resistance in case of the hollow cylinder, that thermal resistance is ln R2 by R1 divided by, that is 2 pi KL. So the thermal resistance concept is very, very important now, that we already saw in the case of the plain ball. Series connection is there, right? So in the case of the series connection, the thermal resistance concept is very, very important. Same here. In case of the hollow cylinder, the thermal resistance is ln R2 by R1 by 2 pi KL, right? So this is the thermal resistance. This is the thermal resistance in case of the hollow cylinder. So temperature variation is logarithmic, and the rate of conduction heat transfer you can calculate by using these mathematical expressions. Is it fine? Now, if there is multi-layer cylinder, or I can say if there is composite cylinder. Composite cylinder means the cylinder is made of more than one material. Cylinder is made of more than one material, right? So let us assume, see, there is a composite cylinder. If I am considering composite cylinder, okay, so this is the composite cylinder. Composite cylinder means cylinder made of more than one material. Okay, now see. Okay. Okay, so let us assume this is a multi-layer cylinder. This is a multi-layer cylinder, or I can say this is a composite cylinder. This is a composite cylinder, right? So this is a cylinder number 1. This is a cylinder number 1. This is a cylinder number 2. This is a center. This radius is R1. This radius is R2, and this radius is R3. This radius is R1. this radius is R2, this radius is R3. The thermal conductivity for cylinder number 1 is K1, thermal conductivity for the cylinder number 2 is, that is K2, right? And at R is equal to R1, the temperature is T1. So here the temperature is T1, here the temperature is T2, and here the temperature is T3, right? And T1 is greater than the T3. T1 is greater than T3. T1 is greater than T3. And I want to find out the rate of conduction heat transfer from this composite cylinder. Rate of conduction heat transfer from this composite cylinder, right? So you can, so we can find out. So this is something like the series connection, right? Series connection. So rate of conduction heat transfer from the cylinder number 1 is equal to rate of conduction heat transfer from the cylinder number 2. So this is a series connection, right? So you can write the thermal resistance. You can write the thermal resistance. Yes, sir, we can write the thermal resistance. So first, that is the thermal resistance of cylinder number 1. This is the thermal resistance of the cylinder number 2. So what is the thermal resistance? Here the temperature is T1. Here the temperature is T3. This is the RTH1. This is the RTH2. And what is the RTH1? That RTH1 is equal to, this is ln R2 by R1 by, that is 2 pi KL. What is the L? L is perpendicular to the monitor. L is the length which is perpendicular to the monitor. What is the RTH2? This RTH2 is ln, and this is R3 by R2 divided by, this is 2 pi, here K1, na? 2 pi K2 L, right? And that is a series connection. So RTH equivalent is equal to, that is RTH1 plus RTH2, right? I want to find out the rate of conduction heat transfer, so that Q dot is equal to, that is T1 minus T3 divided by RTH equivalent, right? So from here you can find out the rate of conduction heat transfer. Is it clear? Now see, if I want to calculate the T2, that is the intermediate temperature T2. So by energy balance we can find out the T2 also, no? Right? I already told you series connection. So Q dot is equal to, that is Q dot 1 is equal to Q dot. So what is the Q dot? That is a T1 minus T3 divided by RTH equivalent, and that is equal to T1 minus T2 RTH1, and this is equal to T2 minus T3, and that is RTH3. Right. So by using this energy balance we can find out the T2 also. Okay. And if let us assume there is another case. So inside this composite cylinder, let us assume a hot gas is passing. And outside the composite cylinder, that is exposed to the ambient. Right? Inside hot gas passes. Let us assume that temperature is TH. The convective heat transfer coefficient is HH. Let us assume. And outside the composite cylinder, or I can say that outside surface is exposed to the ambient. No? So that side, that temperature is TA, and the convective heat transfer coefficient is HA. In this case, let us assume TH is greater than TA. So can we find out the rate of conduction heat transfer? In a similar fashion, we can find out now, series connection only, right? So let us assume that hot fluid passing through this composite cylinder inside hot gas is passing. So that one resistance is add, and that is a convection resistance. Similarly, outside surface is exposed to the ambient now. So again that one convection resistance is added. Is it fine? So in this way you can find out the rate of conduction heat transfer also, right? So if you write the RTH equivalent, so RTH equivalent is equal to RTH of hot fluid plus RTH1 plus RTH2 plus RTH of the ambient air side. Right, so equivalent thermal resistance concept is clear, series connection concept is clear, so there is no need to worry, how to calculate the rate of conduction heat transfer. You just simply write the you just draw the thermal circuit, write the equivalent thermal resistance, right, and by using these concepts, you can find out the rate of conduction heat transfer easily. Okay, so in case of the hollow cylinder, we find the temperature variation, we find the rate of conduction heat transfer, we discuss the multi-layer cylinder, or you can say the composite cylinder. Now next concept is very, very important concept, and that concept is equivalent area concept. And what is that equivalent area concept? Equivalent area concept. So what is the equivalent area concept, right? So in case of the hollow cylinder, what is the equivalent area? So first try to understand what is the equivalent area. What is the equivalent area? Okay. Now see, this radial distance is R1, this radial distance is R2. This is R2, this is R1, right? At R is equal to R1, temperature is T1. At R is equal to R1, the temperature is T1 na? At R is equal to R2, that temperature is T2 na? And T1 is greater than T2. So what is the rate of conduction heat transfer? From this hollow sphere? That is a Q dot. And what is this thickness? This thickness is, let us assume this is the delta. And what is the delta? This delta is R2 minus R1. Perpendicular to the monitor, the length is L, right? And the thermal conductivity of this hollow cylinder is K. Right? So if I want to find out the rate of conduction heat transfer from this hollow cylinder by the concept of the plane wall, right? So for this, I replace this hollow cylinder with a plane wall. In such a way that thickness is same as the hollow cylinder. The thickness of this plane wall is same as the hollow cylinder. That means here that thickness is delta, right? This plane wall is made of the same material, right? That is for the hollow cylinder. That means the thermal conductivity is same. The temperature difference across the surfaces are same. That means here the temperature is T1, here the temperature is T2. The rate of conduction heat transfer, that is also same. That means here the rate of conduction heat transfer is Q dot. So question is that what is the area of this plane wall, and that area is known as the equivalent area. This area is known as the equivalent area. So if I replace the hollow cylinder with a plane wall in such a way that thickness is same, material is same, the temperature difference across the surfaces are same, right? the rate of conduction heat transfer is same. So what is the area of this plane wall? What is the area of this plane wall? Right, that is the equivalent area. That is the equivalent area. Is it fine? Right. So what is the equivalent area? So calculate the equivalent area by this relation. We already discussed, na? The rate of conduction heat transfer from this hollow cylinder is equal to rate of conduction heat transfer this plane wall. So rate of conduction heat transfer through the hollow cylinder is equal to rate of conduction heat transfer through the plane wall. So rate of conduction heat transfer from the hollow cylinder, that is ln R2 by R1 divided by, that is 2 pi, sorry, that is T1 minus T2, T1 minus T2 divided by thermal resistance in case of the hollow cylinder. That is equal to T1 minus T2, T1 minus T2 thermal resistance in case of the plane wall. Right. So T1 minus T2, T1 minus T2 cancel out. So ultimately what you are getting, that thermal resistance of the hollow cylinder is equal to thermal resistance of the plane wall. Right. And what is the thermal resistance for the hollow cylinder? This is ln R2 by R1 2 pi KL is equal to, here this is R2 minus R1, the thickness delta by Ka na. So R2 minus R1, delta is R2 minus R1 by K into A equivalent. So this K and this K is cancelled out. So A equivalent, that A equivalent is equal to R2 minus R1, that is 2 pi L R2 minus R1 divided by ln R2 by R1. Right. So that A equivalent is equal to, right, now this 2 pi L into R2, this is A2, minus 2 pi L R1, this is the A1, divided by, right, here you have to multiply, see that R2 by R1, we can write R2 by R1 like this, na? R2 by R1 is equal to, this is 2 pi L R2 divided by, this is 2 pi L R1. We can write in this way, yes or no? So 2 pi L R2, this is the A2 and this is the A1. Simple. Right, 2 in the numerator multiplied by 2 pi L, in the denominator multiplied by 2 pi L. Right. So R2 by R1 we can write in this way, ln L2 by ln A2 by A1. We can write in this way. Is it clear? So this is the equivalent area. 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 And in this case, in the case of the hollow cylinder, this equivalent area is A2 minus A1 ln A2 by A1. A2 by A1. This is logarithmic mean area. This is the logarithmic. This is the logarithmic mean area of A1 and A2. Logarithmic mean area of A1, A2. Right, there is a arithmetic mean, there is a geometric mean. Similarly, this is the logarithmic mean. The logarithmic mean area of A1 and A2. Right, so in case of the hollow cylinder, this equivalent area is logarithmic mean of inner area, inner surface area and the outer surface area. Is it clear? And what is the significance of this equivalent area concept? What is the significance of this equivalent area concept? See, in case of the in case of the plane wall, right? The plane wall is the simple case. The simplest case is the plane wall, right? So, in case of the plane wall, if I want to calculate the rate of conduction heat transfer, in case of the plane wall, if I want to calculate the rate of conduction heat transfer, here the temperature is T1, here the temperature is T2, the thickness is delta. So that Q dot is equal to, this is T1 minus T2 divided by thermal resistance, and that is delta by K. By using the same concept, we can find out the rate of conduction heat transfer from the hollow sphere also. But the only difference is, instead of this A, you have to write AM. Instead of this A, you have to write the AM. What is the delta? In case of the hollow sphere, in case of the hollow cylinder, what is the delta? That is R2 minus R1 now. The delta is R2 minus R1 now. And what is that AM? This is the equivalent area, and this equivalent area is logarithmic mean area. Right. So this is the significance of the equivalent area concept. So I hope you can understand this part. Okay, so this is the equivalent area. Okay, now come to the next very, very important topic, and that topic is solid cylinder with internal heat generation. So far we are neglecting the internal heat generation. We are not considering the internal heat generation. Right. Now we are discussing a case where that internal heat generation term is there. Right. So I am considering a solid cylinder, and in that solid cylinder, that in a uniform way, that internal heat generation occurs. Right. So the next topic is solid cylinder with uniform heat generation, or solid cylinder with internal heat generation. Solid cylinder with internal heat generation. Solid cylinder with internal heat generation. Okay, now I am considering a solid cylinder. So let us assume this is a solid cylinder. This is the center line. The radius is R. This radius is capital R. And here the temperature is TW. Here the temperature is TW. Okay. And uniform heat generation is there. Uniform heat generation is there, and that is Q dot G. That Q dot G is uniform. I am considering uniform volumetric heat generation. Heat generation, and that unit is watt per meter cube. This heat generation is non-uniform also, na? So first here we are discussing if the heat generation is uniform. If the heat generation is uniform, right? And later on we are discussing if heat generation is non-uniform then. Right. So Q dot G is here uniform volumetric heat generation rate. Okay. And the length, this length is capital L. This length is capital N. This is the radial direction. This is the radial direction. Is it fine? Okay. Now see, in this case, if solid cylinder is there and the internal heat generation is there, so first try to understand what is our objective. Right. If objective is clear, then at least you understand from where, at least you are able to understand from where I am starting. Right. So this is the solid cylinder with uniform internal heat generation. What is the objective? That objective is first objective is find the variation of temperature. First objective is find the variation of temperature. Temperature of variation with respect to what? So first understand the assumptions. So what are the assumptions? That first assumption is material is homogeneous and the isotropic. Assumptions. That first assumption is material is homogeneous and the isotropic. Homogeneous and isotropic. Homogeneous and isotropic. This is the first assumption. Second assumption. The second assumption is one dimensional. one dimension, and in one dimensional that direction is radial direction. That direction is radial direction. What is the third assumption? What is the third assumption? The third assumption is steady state. Third assumption is steady state. What is the fourth assumption? Fourth assumption is thermal conductivity is constant. What is the fifth assumption? Fifth assumption is internal heat generation is uniform. Internal heat generation is uniform. Internal heat generation is uniform. That internal heat generation is uniform. Is it clear? Is it clear? Okay, sir. Now see. If you are considering all these assumptions, then it is very much clear that temperature is only function of R. Steady state, radial direction, internal heat generation is there. So temperature is only function of R. So first I want to calculate how the temperature is changing with respect to R, right? And after that I find the location of maximum temperature and the maximum temperature. This is the objective. Because in this case, whatever the heat generation is there, that is equal to the rate of conduction heat transfer from this solid cylinder, right? So there is no need to worry about the rate of conduction heat transfer, because whatever the rate of heat generation occurs, the same rate of whatever the heat generation occurs, that is equal to the rate of conduction heat transfer from this solid cylinder. Okay, so first objective is find the temperature variation with R. The first objective is find the temperature variation with R, and the second objective is find the location of maximum temperature and the maximum temperature. Okay, so from where we will start, right? We will start from the general heat conduction equation. Right? So under these assumptions, can we reduce the general heat conduction equation in a simple form? Yes, sir. Right. So see, the general heat conduction equation in a simple form, I directly write that is 1 by R d by dr, that is R dt by dr is equal to, plus q dot g by k is equal to 0. Fine. Now see, if you simplify this mathematical expression, R dt by dr is equal to, this is minus q dot g by k into, that is R. Right. Now integrate this mathematical expression. If you are integrating once, what you are getting, that is R dt by dr, and that is equal to R dt by dr, that is equal to minus q dot g into R square by, that is 2k, plus integration constant, that is C1. Right, and this is the equation number A. I say this is the equation number A. Right, now you can arrange this mathematical expression. Dt by dr is equal to, that is minus q dot g into R by 2k plus C1 by R plus C1 by R. Now integrate once again. So what you are getting, that temperature T is equal to, or T of R is equal to minus q dot g by that is R square by 4k plus C1 ln R plus C2. This is the equation number B. Equation number A and equation number B. Now see, C1 and C2 are two integration constant, and to calculate the C1 and C2 there is need of the boundary condition. And what are those boundary conditions? So that first boundary condition, see here, that boundary conditions that boundary condition. What is the first boundary condition? That first boundary condition at R is equal to capital R. See here. At R is equal to capital R. That T is equal to TW now. That T is equal to TW. So this is the one boundary condition. And what is the another boundary condition? That another boundary condition is at R is equal to 0. At R is equal to 0, that is dt by dr is equal to 0. At R is equal to 0, that dt by dr is equal to 0. From where? From the symmetry. From the symmetry. From the symmetry. We already discussed the plane wall with uniform heat generation symmetry case. Remember? Remember that plane wall with uniform heat generation and the case is symmetric. Case is symmetric, that means here the temperature is TW. 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 So the temperature variation is, that is parabolic, and at the center here that temperature is maximum and the temperature is maximum, dt by dr is 0 na. dt by dr is equal to 0 at the center plane, that dt by dr is equal to 0 na. Because of the symmetry. The same thing is here. Due to the symmetry, at R is equal to 0, that dt by dr is equal to 0, right? So if you use the second boundary condition, if you use the second boundary condition at R is equal to 0, that dt by dr is equal to 0, that C1 is equal to 0. So from the second boundary condition, the C1 is 0. From the second boundary condition, the C1 is 0, right? And the first boundary condition, from the first boundary condition, what is the C2? That C2 is, this T is TW, no? TW plus Q dot G R square by 4K, because this term is 0, no? C1 is 0. So from the second boundary condition, from the first boundary condition, the C2 is equal to TW plus Q dot G R square by 4K, and from the second boundary condition, the C1 is equal to 0. So ultimately what you are getting, right? If you are putting this C1 and C2 in the equation number B, then what you are getting? You are getting this. T of R is equal to, that is TW plus Q dot G by 4K, and that is capital R square minus small r square. See, this is the temperature variation with R. This is the temperature variation with R. This is the temperature variation with R. And from this expression, it is very much clear that temperature is changing with respect to R parabolically. Second degree parabola. Second degree parabola. And where the temperature is maximum? Where the temperature is maximum? At R is equal to 0. At R is equal to 0, the T become T max. T max. So what is the T max? The T max is equal to, this is TW plus Q dot G by 4K R square. This is the T max. This is the T max. Is it clear? So how the temperature varies? Let's see how the temperature varies. So this is the solid cylinder, na? This is the solid cylinder. Now see, here the temperature is TW, here the temperature is TW, here the temperature is maximum, na? Here the temperature is maximum, see. See, this is the temperature variation. This is the temperature variation. Okay, that is second degree parabola. Second degree parabola. That temperature variation is second degree parabola. Is it clear? Is it clear? Okay, now see, if non-uniform heat generation is there, then where the changes occurs? If the non-uniform heat generation is there, non-uniform heat generation is there. So if the non-uniform heat generation is there, then where the changes occurs? The changes occurs here, right? If suppose, let us assume this Q dot G is given like this. Q dot G is given like this. This is the Q dot naught 1 minus small r square by capital R square. If Q dot G is given like this, right? That means in this expression, it is clear that the rate of internal heat energy generation, or I can say the volumetric heat generation, is function of R. So that is non-uniform heat generation. So where the changes occur? The changes occurs here, right? You put this relation here and accordingly perform the mathematical things, right? That is the only change, right? So if non-uniform heat generation is there, then that mathematical expression is not, this mathematical expression is not applicable now. If that volumetric heat generation is non-uniform, then this mathematical expression is not applicable. Is it fine? And similarly, this is the case of the non-uniform heat generation, right? In case of the non-uniform heat generation, this mathematical expression is not applicable. This mathematical expression is applicable when solid cylinder is there and the uniform internal heat generation is there, and apart from that, the assumptions we already considered. Is it fine? And let us assume if there is a hollow cylinder with internal heat generation, with uniform internal heat generation. If there is a hollow cylinder, so I roughly draw now. Right, this is the hollow cylinder, and in this hollow cylinder, that uniform heat generation is there. Here the temperature, let us assume I am considering T1. Because of this internal heat generation, this phase has a temperature T1, and let us assume I am considering that inner phase is adiabatic. I am considering this inner phase is adiabatic. So this is the radial distance R1, this is the radial distance R2. This is the radial distance R1, this is the radial distance R2. Right. So this is the hollow cylinder with uniform internal heat energy generation. So again, the mathematical expression, right, that mathematical expression we derived just few time back, right, that mathematical expression is not applicable here. Right, that means I can say this mathematical expression is not applicable here, because this is a hollow cylinder with uniform internal heat generation case. Right. So again, where the change occurs, see, in this case, if uniform heat generation is there now, till here, equation A and equation B is same. The only changes that occurs that is in boundary condition. And I already discussed the boundary condition is always according to the problems. Boundary conditions are always according to the problem. See the problem carefully, right, and find the boundary condition, right? So in the case of the hollow cylinder, with uniform internal heat generation, what is the boundary condition? So it is clear here at R is equal to R1, the T is equal to T1, or I can say this is the TW. At R is equal to capital R1, the T is equal to TW. And what is the second boundary condition? The second boundary condition is at R is equal to, this is R2. At R is equal to R1, the rate of conduction heat transfer, because that surface is adiabatic, so rate of conduction heat transfer at R is equal to R1 is 0. So directly we can say that dt by dr at R is equal to R1, that is equal to 0. Because rate of conduction heat transfer, you write that minus Ka dt by dr, so K is not equal to 0, A is not equal to 0. So what is the dt by, what is 0? The dt by dr is 0. So dt by dr at R is equal to R1 is 0. So these are the two boundary conditions. Right, that only changes that occurs in the boundary condition. I hope you can understand this. Right, so this is the standard, I can say this is the standard mathematical expression, right, solid cylinder with internal heat generation. But if solid cylinder with non-uniform heat generation, then you solve the problem accordingly, right. If there is a hollow cylinder with uniform heat generation, then solve the problem accordingly. Is it clear? Okay, so this is all about the cylindrical coordinate system, hollow cylinder, solid cylinder with internal heat generation. Now next topic is first understand the spherical coordinate system, right? Then we will discuss about the general heat conduction equation in the spherical coordinate system, right? Now let's start our discussion on spherical coordinate system, right? So first try to understand if I want to locate a point in a spherical coordinate system, then what parameters are required, right? So first understand this thing, spherical coordinate system. Spherical coordinate system. Spherical coordinate system. Spherical coordinate system. Okay. So in case of the Cartesian coordinate system, x, y, z is required. In case of the cylindrical coordinate system, r, phi and z is required. In spherical coordinate system, what parameters are required? What parameters are required? Right. So in spherical coordinate system, that r, phi and theta. R, phi, theta. What is the r? That r is a radial distance. What is a phi? Phi is an angle in the circumferential, in a horizontal plane. In a horizontal plane, right? And what is a theta? That theta is a, right? The theta is an angle in a vertical plane. Okay. So let's discuss this part first. So I am considering a sphere. I am considering a sphere. So this is a sphere. This is the sphere. This is a sphere. And in this sphere, I want to locate a point. So this is the z, sorry, this is the z direction. This is the y direction. And this is the x direction. So this is the xy plane, this is the yz plane. That yz plane is a vertical plane and the yx plane is a horizontal plane, right? I want to locate a point in this spherical coordinate system, right? So first I want to, first I fix the radial distance. That first I fix the radial distance. See that point may be at any radial distance now on this sphere. That sphere may be of radius 10 centimeter, maybe of radius 20 centimeter, maybe of radius 50 centimeter. So that point is at any radial distance. That point is at any radial distance, right? That point is at any radial distance. So first fix the r, right? And what is the limit of the r? That limit of the r is 0 tends to infinite. The limit of the r is 0 tends to infinite. Okay. Now focus on the horizontal plane, right? Horizontal planes means xy plane, and in xy plane you are observe the circle, no? So this is a circle in xy plane. Right, this is the y-axis and this is the x-axis. Now see here. First let us assume this is a sphere. Let us assume this is a sphere. First you understand in this. Okay, let us assume this is a sphere and I want to locate a point on this sphere. Let us assume I want to locate this point on this sphere. Okay. So to locate this point, what parameters are required? So first understand the radial distance is required, the radius is required. This sphere may be of radius 10 centimeter, 20 centimeter, 50 centimeter or whatever it is. So first fix the radial distance, first fix the radius, right? This sphere may be of 10 centimeter, maybe of 50 centimeter. So first fix the radius. So I fix the radius, and what is the limit of the radius? The radius limit is 0 tends to infinity. Is it fine? Okay. Now see here. If you fix the radius, then in a horizontal plane, okay, how you see the horizontal plane? Cut this sphere. Let us assume this is a sphere. Na? This is the sphere. Don't say, sir, this is not a sphere. Let us assume this is a sphere, right? Now see, cut this sphere horizontally. Cut this sphere horizontally. So you are easily understand the horizontal plane. And in horizontal plane, right, what you are observed? You observe a circle. You observe a circle. So this is a circle of horizontal plane. Horizontal plane, that means xy plane. Okay. Now see, if you fix the r, then this point in a horizontal plane, that is a circle, right? That point may be here, 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 that point may be here. At fixed r, this point may be anywhere, na? Is it fine? In a circumference, in a horizontal plane, right? You observe a circle, and in the circumference of the circle, this point may be anywhere near. So for this, I define a parameter which is phi. Right? So this is the circle of horizontal plane. This is the circle of horizontal plane circle. Right? And this is the xy plane. So phi is 0 at the x-axis. And this point may be anywhere, na? This point may be anywhere, na? So what is the limit of the phi? The limit of the phi is 0 to 2 pi, na? 0 to 2 pi. The limit of the phi is 0 to 2 pi, na? Is it clear? So in a horizontal plane, if I want to fix a point, then r and phi is required. But in a space, that another parameter is required. In a space, there is another parameter is required. Now see here. If I fix the r, if I fix the phi, I fix the r. Now see, I fix the r and I fix the phi. So let us assume in a plane, this is the point. Now I want to locate this point in a space. Now see here. If you cut this sphere vertically, then you observe the vertical plane, na? And in vertical plane, again you observe a circle. And that point may be anywhere on a circle, on a circumference of a circle that is in the vertical plane. That means I see here. I fix the r, I fix the phi. Now this point is here, maybe here, maybe here, maybe here, maybe here. This point may be here, maybe here, maybe here. So in a vertical plane, again you are observing a circle. In vertical plane, again you are observing a circle. So first cut the sphere horizontally. You observe a circle in a horizontal plane. Then cut the sphere vertically. You are observing the circle in a vertical plane. Now I am talking about the circle in a vertical plane. And what is the vertical plane? That vertical plane is YZ plane. Vertical plane is a YZ plane, right? So this is the circle that is in vertical plane. Okay. Now see, this is the z-axis and this is the y-axis. Right, this is the z-axis and this is the y-axis. Right. Now see, in the vertical plane, circle is observed, na? And circumference of this circle, this is the circumference, na? This is the circumference. And that point may be here, that point may be here, that point may be here, that point is anywhere, na? So for this I am considering another parameter, and that parameter is theta. So for the theta, the reference is z-axis. So at the z-axis, the theta is equal to 0, and that point may be here, that point may be here, that point may be here. Let us assume this angle is theta. This angle is theta, right? And in a horizontal plane, if point is here, this angle is phi. This angle is phi. Is it fine? So this is the circle in vertical plane. So in a vertical plane, you are observing a circle. In a horizontal plane, you are observing a circle. In horizontal plane, to locate a point, the phi is required, r is fixed. So I am not talking about the r that much. In a horizontal plane, to fix the point, phi is required. In a vertical plane, to fix the point, theta is required. And in the space, phi is also required, theta is also required, right? So in case of the spherical coordinate system, to locate a point, radial distance r, phi, theta is required. Is it clear? Theta is known as the zenith angle. Theta is also called zenith angle, right? This theta, this vertical plane angle, that theta is called zenith angle. Zenith angle, right? And this phi, right? Phi, angle in horizontal plane, this is called azimuthal angle. Azimuthal angle. Azimuthal angle. Is it clear? Right. So if it is clear, then you can easily understand the temperature variation in spherical coordinate system, because right, in a spherical coordinate system, the temperature may vary in radial direction, the temperature may vary in the phi direction, the temperature may vary in the theta direction. Okay? That means the temperature, see here, again I am considering this sphere, this is the, again I am assuming this is the sphere. So temperature vary in a radial direction, temperature vary in this direction, temperature vary with phi, the temperature vary with theta. Is it fine? Is it fine? So in case of the spherical coordinate system, the temperature is function of r, phi, theta, and time tau. Okay, so I write the general heat conduction equation in the spherical coordinate system. So again, from where I start, from the energy balance, right? If you solve the energy balance, then ultimately you are getting this general heat conduction equation, right? So I am writing the general heat conduction equation in the spherical coordinate system. So that is 1 by r square del by del r kr r square del t by del r plus 1 by r square sine square theta del by del phi k phi del t by del phi, right, plus 1 by r square sine theta del by del theta k theta sine theta del t by del theta plus q dot g is equal to, that is rho into c del t by del tau, rho into c del t by del tau. Is it clear? Right. So this is the general heat conduction equation in the spherical coordinate system. That first term shows the temperature variation with r. The second term shows the temperature variation with phi, that means in a horizontal plane. Right. The third term shows the temperature variation with theta, that means in vertical plane. That fourth term shows the internal heat generation term, and the fifth term shows the temperature variation with time. So if I am assuming that material is homogeneous and isotropic, if I am assuming that material is homogeneous and isotropic, if I am assuming that material is homogeneous and isotropic, right? So I write na that Kr is equal to Kr is equal to K phi is equal to K theta. That Kr is equal to K phi is equal to K theta is equal to that is K. That is K. Right. So ultimately what you are getting this 1 by R square del by del R square del T by del R plus 1 by R square sin theta, 1 by R square sin square theta del square T by del phi square plus 1 by R square sin theta, right, del del theta sin theta del T by del theta plus Q dot G by K is equal to 1 by alpha del T by del tau. 1 by alpha del T by del tau. Is it clear? So this is the general heat conduction equation if we assume the material is homogeneous and the isotopic. Okay. Now, again from here you can write the Laplace equation. You can write the Laplace equation. You are able to write the Poisson equation. You are able to write the diffusion equation. What is the Laplace equation? Steady state without internal heat generation. What is the Poisson equation? Steady state with internal heat generation. And what is the diffusion equation? Unsteady state without internal heat energy generation, right? So from here you can easily write the general heat, you can easily write the Laplace equation, Poisson equation and the diffusion equation. We already discussed this part in the Cartesian coordinate system also, in the cylindrical coordinate system also. Okay. Now see, I am assuming or I am taking certain assumptions. What are the assumptions? I want to reduce this general heat conduction equation. I want to reduce this general heat conduction equation in a simple form. So for that assumptions are required. And what are the assumptions? The first assumption is material is homogeneous and isotopic. The second assumption is one dimensional. Second assumption is one dimensional. And in one dimensional, the direction is radial direction. Radial direction. The second assumption is steady state. The second assumption is steady state. The third assumption is no internal heat generation. No internal heat generation. That fourth term is thermal conductivity is constant, not function of temperature. Okay. Now see, under these assumptions, we can write the general heat conduction equation in a simple form. If one dimension, then this term is vanished, this term is vanished. No internal heat generation, that means this term is finished. Steady state, that means this term is finished. So ultimately what you are getting the mathematical expression. Okay, so under these mathematical expression, temperature is only function of R. Temperature is only function of R. So partial derivative is converted into total derivative. So that is 1 by R square d by dr, and this is R square dt by dr. And that is equal to 0. So this is a general heat conduction equation under certain assumptions, right? And this equation we can write in this way also, no? This equation we can write in this way also, right? 1 by R square. Now differentiate these terms, right? So R square constant dt by dr. R square constant differentiating dt by dr. So this is d square t by dr square plus, right? Differentiate R square. So this is 2R and constant dt by dr. And this is equal to 0. Differentiation of uv, right? U constant, differentiate v. V constant, differentiate u, right? So ultimately what you are getting, this is d square t by dr square plus, right? Now this is 2 by r. 2 by r dt by dr is equal to 0. So this equation you can write in this form also, right? This equation you can write in this form also, right? So sometime in exam, expression is given in this form. So you remember this form also. Okay, fine. Now, I want to find out the temperature variation with respect to R. So for this, integrate this expression. Integrate this expression. So if you are integrating, what you are getting, that d by dr, right? First, simplify this. D by dr is equal to, I write here, that is d by dr, and that is r square dt by dr is equal to 0. Is equal to 0, na? Okay. Now integrate. So if you are integrating this, so what you are getting, this r square dt by dr is equal to, that is integration constant, that is C1, right? Now again then simplify it. Dt by dr is equal to, that is C1 by r square. Then again integrate. So if you are again integrating, then what you are getting, that t by r, t of r is equal to, this is r to the power minus 2. So minus 2 plus 1 upon minus 2 plus 1. So this is minus C1 by r plus C2. Okay. So this is the temperature variation with respect to R, C1 and C2. C1 and C2 are integration constant. C1 and C2 are integration constant, which are calculated by using the boundary conditions. Okay, and boundary conditions are according to the problem. Okay, now I am taking another case, and that case is hollow sphere. Hollow sphere. I am considering a case of hollow sphere. Hollow sphere, right? So this is the hollow sphere. Okay. Now this is a hollow sphere, and this radius is R1, this radius is R2, this radius is R1, this radius is R2, and any radial distance, that is R. Any radial distance, that is R. Thermal conductivity of this hollow sphere, that is K, right? And at R is equal to R1, at R is equal to R1, the T is equal to T1. At R is equal to R2, the T is equal to T2. The T is equal to T2. Fine. And T1, I am assuming this T1 is greater than T2. T1 is greater than T2, and at any radial distance, at any radial distance R, at any radial distance R, at any radial distance R, temperature is T. Temperature is T. Temperature is T. Okay. Now see, assumptions are same. Okay, assumptions are same. Assumptions are same. These are the assumptions. Assumptions are same. Okay. So if assumptions are same, then directly we can start our discussion from here, because in this case, okay, in this case, I want to find out the two things. That first thing is temperature variation with R. That first thing, temperature variation is R, temperature variation with R, and the second thing is rate of conduction heat transfer from this hollow sphere. The second thing is rate of conduction heat transfer from this hollow sphere. Okay, so first find the temperature variation with R. To find out the temperature variation with R, I directly start from here. The T of R is equal to, this is the minus C1 by R plus C2. So two boundary conditions are required, and two boundary conditions are here at R is equal to R1, T is equal to T1. T1 minus C1 R1 plus C2. The second boundary condition is T2 is equal to T2, and that is minus C1 by R2 plus C2. Okay, solve these two boundary condition and find the C1 and C2. Solve these two boundary condition and find the C1 and C2. C1 and C2. So after finding the C1 and C2, what is the temperature variation with R? So ultimately you are getting this mathematical expression. So I directly write T of R minus T1 divided by T2 minus T1, and that is equal to 1 by R minus 1 by R1 divided by 1 by R2 minus 1 by R1. Right, so this is the temperature variation with R, and from here it is clear that the temperature variation with R is hyperbolic. Hyperbolic. The temperature variation with R is hyperbolic variation. Okay, temperature variation with R is hyperbolic. Right, so if you see the temperature variation, so here the temperature is T1, here the temperature is T1, here the temperature is T2. So this is the temperature variation, and this temperature variation is, this temperature is T1, this temperature is T2. So this temperature variation is hyperbolic. Hyperbolic temperature variation. Hyperbolic temperature variation. Is it fine? Is it clear? Okay. Now, so first objective is find the temperature variation with R. So temperature variation with R is hyperbolic. Temperature variation with R is hyperbolic. Now second objective is find the rate of conduction heat transfer. So to find out the rate of conduction heat transfer, consider a small elemental area like a hollow cylinder. Consider a small elemental area, right? And from that small elemental area, the rate of conduction heat transfer is dq dot. Apply the Fourier law of heat conduction, right? Apply the Fourier law of heat conduction. Then ultimately what you are getting, I am writing directly that thing. I am directly writing that thing, because that procedure is exactly same as the hollow cylinder. Procedure is exactly same. The only changes that is there, the only changes is, right, only changes is temperature variation. Here the temperature variation is hyperbolic. In the case of the hollow cylinder, the temperature variation is logarithmic, right? So if you apply the Fourier law of heat conduction, that q dot is equal to, that is minus Ka, and this is dt by dr. Directly I apply, na? I'm not showing the small elemental area, right? Because I already told you that is exactly same as the hollow cylinder, right? So that is minus Ka dt by dr. From here you can find out the dt by dr. From here you can find out the dt by dr. From here you can find out the dt by dr. And what is the area from where the conduction occurs? That is the surface area of the sphere, and that is 4 pi, right? That is 4 pi r square. That is 4 pi r square. Right, at a radial distance r, I am considering a small elemental area. At a radial distance r, I am considering a small elemental area, right? And the conduction heat transfer occurs from the surface area of that small elemental area, right? So what is the surface area of that small elemental area? That is 4 pi r square, na? Okay, so A is 4 pi r square. dt by dr you are calculating from here. So ultimately what you are getting? Ultimately what you are getting this mathematical expression. The rate of conduction heat transfer, that is T1 minus T2 divided by, that is R2 minus R1 4 pi K R1 R2, 4 pi K R1 R2. And if you are comparing this mathematical expression with T1 minus T2 by RTH, so ultimately you are getting the RTH also. That means thermal resistance in case of the hollow sphere, and that is R2 minus R1 divided by 4 pi k R1 R2. So this is the thermal resistance in case of the hollow sphere. Okay, and if there is a problem which is based on the composite sphere, or I can say multi-layer hollow sphere, right? So you can easily calculate the rate of conduction heat transfer on that case also, right? If I am considering multi-layer sphere, that means see, like this. Okay, so this is the hollow sphere 1, this is the hollow sphere 2. Here the thermal conductivity is K1, here the thermal conductivity is K2. This is the radial distance R1, this is the radial distance R2, and here the radius is R3. Okay, and here the temperature is T1, here the temperature is T3. And if I am saying that T1 is greater than T3, T3. So what is the rate of conduction heat transfer? So first draw the thermal resistance, right? Then find out the equivalent thermal resistance. After getting the equivalent thermal resistance, find out the rate of conduction heat transfer. So rate of conduction heat transfer, that Q dot is equal to, that is T1 minus T3 divided by RTH equivalent. And what is the RTH equivalent? That is a series connection. Na? So series connection, first, this is the thermal resistance of sphere 1, this is the thermal resistance of sphere 2, right? Here the temperature is T1, here the temperature is T3, here the temperature is T2, right? This is the RTH1, this is the RTH2, right? The same thing we already discussed in the multi-layer cylinder also, या फिर composite cylinder also, right? So this is the case of the composite sphere. The only difference is the expression of the thermal resistance. That only difference is expression of the thermal resistance, and here that RTH1 is R2 minus R1. This is 4 pi K1 R1 R2. And what is the RTH2? That RTH2 is R3 minus R2 divided by, this is 4 pi K2, and this is R1 R2. Right, this is the only difference. And if I want to calculate the intermediate temperature, so to calculate the intermediate temperature, that energy balance is there, no? Energy balance. That Q dot is equal to Q dot 1 is equal to Q dot 2. What is the Q dot 1? T1 minus T2 by RTH1. And what is the Q dot 2? T2 minus T3 divided by RTH2. And what is the Q dot? That Q dot is T1 minus T3 divided by RTH equivalent. Same as the hollow cylinder, same as the composite cylinder. Okay, so this is the composite sphere. So I think this is clear. This is composite sphere. If a sphere is made of more than one material. If a sphere is made of more than one material. Is it fine? Is it clear? Okay. Now come to the next topic. Next topic is very, very important, right? That solid sphere with internal heat generation, right? Solid sphere with internal heat generation. Okay, no, but before that, that equivalent area concept, right? In case of the hollow cylinder, that equivalent area is equal to logarithmic mean area. Now, in case of the hollow sphere, what is the equivalent area? What is the mathematical expression of the equivalent area? Concept is same. What is the mathematical expression for the equivalent area in case of the hollow sphere? So, equivalent area, right? Equivalent area. What is the equivalent area expression? What is the equivalent area expression for the hollow sphere? So hollow sphere, so let us assume this is the hollow sphere. I draw roughly, no? Okay. this radius is R1, this radius is R2, here the temperature is T1, here the temperature is T2, rate of conduction heat transfer is Q dot, thickness, that thickness delta is equal to R2 minus R1, right. I replaces this hollow sphere with a plane wall, having same thickness delta, material is also same, so thermal conductivity is also same, temperature across the surfaces, that is also same, rate of conduction heat transfer, that is also same. So what is the area of this plane wall? And that area is known as the equivalent area. So what is the equivalent area? So in case of the hollow sphere, that Q dot hollow sphere is equal to Q dot plane wall, right. So that is T1 minus T2 divided by RTH hollow sphere, and that is T1 minus T2 divided by RTH plane wall, right. So T1 minus T2 finish, right. RTH hollow cylinder, and that is 4 pi k, I say 4 pi k, that is reciprocal na 1 by RTH. So that is 4 pi k R1 R2 divided by, that is R2 minus R1 is equal to, right, that is delta by k. So this is k A equivalent, and this is R2 minus R1, right, R2 minus R1 k. So ultimately that equivalent area is equal to, this is 4 pi R1 R2. Okay, so you can write this mathematical expression in this way also. A1 is 4 pi R1 square, no? A1 is 4 pi R1 square. A2 is 4 pi R2 square. So A1 A2 is 16 pi square R1 square R2 square. So root over A1 A2 is equal to, that is 4 pi R1 R2, 4 pi R1 R2. So what is the equivalent area? This equivalent area is equal to, this is root over A1 A2, and this is nothing but the root over A1 A2, that means it is geometric mean, na? It is root over A1 A2, so this is a geometric mean, na? Geometric mean of A1 and A2, geometric mean of A1 and A2. So in this case, in the case of the hollow sphere, what is the equivalent area? Geometric mean of A1 and A2. In case of the hollow cylinder, what is the equivalent area? That is the logarithmic mean area. Is it clear? Right. So that is the equivalent area concept for the hollow sphere. And what is the significance? That already I discussed in the cylindric, in the case of the hollow cylinder. The same significance is here. Okay. Now come to the next. And that is a solid sphere with internal heat generation. Solid sphere with internal heat generation. Okay, now see. So first I am considering a solid sphere. So this is the solid sphere. This is a solid sphere, and that radius of this solid sphere is, that is capital R, and here the temperature is TW. At R is equal to capital R, the temperature is TW, and that uniform heat generation is there and that is a Q dot G. In this sphere, that uniform heat generation is there, right? So what are the assumptions? That assumptions, write the assumption first. What are the assumptions? So that first assumption is one dimensional, and in one dimensional that direction is radial. The second assumption is steady state. The third assumption is uniform internal heat generation. I am assuming here that heat generation is uniform heat generation. Uniform heat generation. What is the fourth assumption? What is the fourth assumption? That fourth assumption is thermal conductivity is constant. That fourth assumption is thermal conductivity is constant. Is it fine? So what is the Q dot G? This Q dot G is volumetric heat generation rate, or you can say that uniform volumetric heat generation rate. Uniform volumetric heat generation rate, and that is in watt per meter cube. That is in watt per meter cube. Okay, so under these assumptions, can you write the general heat conduction equation? Yes, sir, we can write V by R square d by dr R square dt by dr plus Q dot G by K is equal to 0. So if you simplify this mathematical expression, so d by dr R square dt by dr, that is minus Q dot G by K, minus Q dot G by K into R square, minus Q dot G by K into R square. Right, now integrate. So if you are integrating, R square dt by dr is equal to, that is minus Q dot G by, this is the R cube by 3K plus, that is C1. Right. So again, if you are simplifying it, dt by dr is equal to, that is minus Q dot G R by 3K plus, that is C1 by R square. C1 by R square. Now integrate once again. Right, so I said this is the equation number A, na? This is the equation number 1. Right, now what I am doing here, I find the C1 first. So to find out the C1, can we use the boundary condition? What is the boundary condition? At R is equal to 0, that dt by dr, at R is equal to 0, that dt by dr is equal to 0. Can we use this mathematical expression? This is the radial direction, na? This is the radial direction. So at R is equal to 0, that dt by dr is equal to 0 from the symmetry. Right, from the symmetry we can write directly, na? Right. So here at R is equal to 0, that dt by dr 0. So from this mathematical expression, see this mathematical expression, the C1 is equal to 0. So ultimately what you are getting this dt by dr is equal to, that is minus Q dot G into R by, that is 3K. Right. Now integrate once again. If you are integrating once again, then this is minus Q dot G, this is R square by 6K plus integration constant, that is C2. So to calculate the C2, use another boundary condition, and that is at R is equal to capital R, the T is equal to TW. So ultimately what you are getting, that is TW is equal to, this is TW plus Q dot G by 6K capital R square, and this is C2. Right. By using this boundary condition, you are able to find out the C2. Now put the value of C1 and C2. put the value of C1 and C2 on this mathematical expression. So this is the equation number B. Put the value of C1 and C2 on the mathematical expression number B. So from B, from equation B, what you are getting? You are getting this. T of R is equal to, this is TW plus Q dot G by 6K capital R square minus small r square, right? And that variation is second degree parabola. The temperature variation is second degree parabola. So the mathematical expression is same as the solid cylinder with the internal heat generation. That only difference is, right, in case of the solid cylinder with internal heat generation, here the factor is 4. Here the factor is 4. Instead of the 6, there is 4. Here that is 6. That is the only difference. Right, and where the maximum temperature you are getting? At R is equal to 0, the T becomes T max. So what is the T max? The T max is equal to, this is TW plus Q dot G by 6K. R square. So this is the T max, and this is the variation of temperature with R. Okay, so I hope this is clear. So this is the solid sphere with internal heat generation. If the heat generation is non-uniform, then that already discussed in the cylindrical coordinate. I already discussed in the solid cylinder with internal heat generation. If heat generation is non-uniform, then how you proceed? We already discussed. If there is a hollow sphere with uniform heat generation, then how you are dealing that problem? Same as the hollow cylinder with uniform internal heat generation, that I already discussed. So you can say there is analogy between the cylindrical coordinate system and the spherical coordinate system. If you understand the cylindrical coordinate system thoroughly, if you understand the how we find the temperature variation with respect to R, how we find the temperature variation with respect to radial direction, how we are calculating the rate of conduction heat transfer, right? How we are dealing with the solid cylinder with internal heat generation, you can easily understand the all the cases in the spherical coordinate system, right? Hollow sphere, solid sphere with internal heat generation. If there is a hollow sphere, then if internal heat generation occurs, then how you deal, right? If there is a solid cylinder but non-uniform heat generation, then how you deal, right? That is exactly same. Is it clear? So we can say there is an analogy between the cylindrical coordinate system and the spherical coordinate system. Okay, so I hope this is clear to everyone. So this is all about the steady state conduction heat transfer in the spherical coordinate system and in the cylindrical coordinate system. Okay, is it okay? Yes or no? Is it okay? Tell me guys, is it okay? Okay, so this is all about the cylindrical coordinate system and the spherical coordinate system. So thank you so much guys. Thank you so much. Bye bye. Take care and have a good day.